Okay, about the pre-reports. I mean, just around the hours of the deadline of the pre-report, I receive getting all these emails about the problems that you face, about uploading the pre-reports, which I happily ignore. I mean, if you have preferred to leave uploading your pre-reports to the last minute or last second, then you are accepting all the consequences of the things that can go wrong, like your computer might stop working, your internet connection might break up, etc. So if you don't want to face these problems, upload your pre-reports before the deadline. And don't send me emails just on the day of the deadline. Okay, any questions about the momentum conservation? Okay, yes.
Yeah, in solving this problem, how do you do it? You can, for example, if I, based on what's on the exchange there, that the golf ball moving, let's compare with that distributed is the golf, right? The golf ball moving up with that velocity and the distributed moving down that way.
And this one, yes.
So, because I know, basically, if I choose something against that ball, it's going to.
This way here.
Let's assume we choose something against this ball.
Here. Okay.
If you choose something against the ball, you realize that the change in momentum of the ball after collision with the ball will be twice.
Okay.
Okay. Now, so in that case, can I do this thing? I'll just take the. So because I know the scenario, I'm going to get confused with the ball having an initial velocity. So I'll try and, like you said, moving the ball, the golf to an initial reference frame where it's zero.
Okay. Okay, so it's at rest.
When I try moving it to initial reference frame zero, I have to increase the velocity of the ball. If the tennis ball is moving down and the golf is moving up, the change in now the current, the new velocity of the tennis will be negative v minus negative v prime. If v represents the velocity of the tennis, and then v prime represents the velocity of the ball.
Okay.
If I take my reference frame where the golf is zero, it means that the negative v minus negative minus v prime.
I'm having difficulty which reference frame you are talking about. So, okay, so your question?
So my question is, initially, can I use a reference frame where v prime is zero? That if v prime is the velocity of the ball.
Now, you can use whichever reference frame you like. Now, in particular, this means that you can set the velocity of any object to zero at one instant in one particular reference frame. You can always choose such a reference frame. And this is what we used over here. I can always go to a reference frame in which the golf ball is at rest during the collision. It doesn't stay at rest throughout its motion, but at least during the collision, which we assume is almost instantaneous, it will be at rest. I can always do that.
So, but eventually I have to bring it back to the...
Because I want to study the problem in this. This is the reference frame that I'm observing my surrounding. So that's why I wanted to go eventually to this reference frame.
But is it necessary to have to take it back to the original reference frame?
Well, it depends on what you want to answer. My question is, this is what I wanted to explain, this observation. So how high would that go in the ideal case that it just goes straight up? Well, I'm already in this reference frame.
It will depend on the reference frame.
Sure. Sure.
Okay, so eventually can I, that's the I'm solving the question. If I need to state the reference frame I'm considering, right?
Sure. Now you always have to specify which reference frames you are working in. Other questions? No questions? Okay, now there was one topic which we kind of passed quite fast. the center of mass. We already defined what we mean by the center of mass. And our definition of the center of mass was if we have, let's say, a bunch of objects, let's say each, they have their positions, or 1, or 2, or 3. Let's say this is our I. This has a mass mi, this has a mass m1, m2, m3, etc. Then we had defined the position of the center of mass to be mi times our I multiplied with 1 over the total mass. Now, one thing is, how do you find the center of mass? Can you find the center of mass of this object? I mean, if you put the object in the center of mass, if you hold the object at the center of mass, it should stay at rest, right? So show me the middle. Okay, you are somewhat close, but, well, kind of, well, you are moving your finger all the time. Okay, finding the center of mass usually will not be that easy. Now, one trick, especially if you have such an object, is rather than trying to put it in the center of mass, just hold your fingers, bring them together, and here is the center of mass. It will always work. Okay, why that trick works, we will cover it in a couple of weeks. Now, that is one way of finding the center of mass. Now, another way, if you have an arbitrary shaped object, just hang it from the wall. You say, this is my object. Just hang it from this side. Now, the center of mass of this object will be on this line. Because if you hold it like this, it just rotates. If you hold it like this, it rotates. It won't rotate only when the center of mass is just below this string. And if you just take it and hang it from some other point, now this is the same object, believe it or not. If you hang it like this, it will. If it stays like in this shape, this is the position of the center of mass. Now, this is how you can measure the center of mass. Now, another thing is we will be interested in calculating the center of mass of objects. Of course, if it is just two masses, then we already know that if we have mass 1 over here, mass 2 over here, the center of mass is somewhere along this line. At this point, our center of mass, we already said that this was m1 r1 plus m2 r2 divided by m1 plus m2. Now, the problem is, what if we have a larger object, not just a collection of points? What is the center of mass of a disk? It's not just a bunch of point masses. So how do we calculate the center of mass of such an extended object? Any suggestions? Are you sure? How can you show that it is the center? Somebody else?
I'll try to hang it on the...
Okay, so that is how we measure it. We want to calculate it.
We divide them to the infinite circles.
Okay, infinite circles. So your friend is saying that, okay, this is not point objects, but I can assume that this is a collection of smaller objects. So each one of these rings are smaller. This is one. This is the other one. So I can just treat it as a collection of these smaller objects. But nevertheless, what is the center of mass of each one of these rings?
Each one of these rings, the opposite ones, if opposite ones will cancel each other at the middle point. That's right, it's the middle point.
So we have this ring. Where is the center of mass?
Do we know that it's uniform density?
Well, that is a critical thing, which you seem to be ignoring. Let's say your other friend had a point. Let's just take opposite points. Let me just divide, still this is not point objects. The center of mass we define to be equal to this one for point-like objects. This is not point-like, but I can still divide it into very small point-like objects. Now, I will take them to be smaller and smaller and smaller, so they are almost point-like. Then I can just consider, let's say, two diametrically opposite points. Now, let's say this has length dl. This also, let's say, has length dl, the length of the arc. Let's just assume that mass is homogeneous. So this has mass dm. This also has mass dm. This dm is just a very small amount of mass. Now, what is the center of mass of these 2 points only? Now, the center of mass of this one and the center of mass of this other one. Or we can even consider the other masses. Our center of mass will be dm. We can just take any point that you like as your origin. Let's just take the center for simplicity. X-axis, y-axis. So this is my R1. This is my R2. The center of mass of the whole system will be just the sum of dm times Ri divided by the total mass. dm, I'm just assuming that all of them, well, let's see. This one has the x and the y components, Ri. But if you look at these 2 points, the x-coordinate of this one and the x-coordinate of this one, they are just in opposite directions. The y-coordinate of this one and the y-coordinate of this one, they are also in opposite directions. They have the same magnitude, but in opposite directions. So the x-coordinate of this one plus the x-coordinate of this one gives me 0. The y-coordinate of this one, the y-coordinate of this one gives me 0. It will be true for each one of these segments. For every segment over here, there will be a corresponding segment over there. When I sum their position vectors, I will just get to 0. So summing all of them, what I get is just 0. So if I have this ring, the position of the center of mass of this ring, assuming, of course, that the mass is uniformly distributed, because with this assumption, I know that this dm is equal to 0. dm is constant, so I can just take it out. If mass was not homogeneous, this is no longer true. This is only true if the mass is homogeneous. It's homogeneously distributed. So I know that the center of mass of this object is 0, is at the origin. Now let's come back to this one. What will be the center of mass of this whole thing? Now, still I have one more problem to solve if I want to calculate the center of mass of this whole thing. I know the center of mass, I know how to calculate the center of mass from point objects. Now I had already solved one part of the problem. I know that the center of mass of such a ring is just its geometrical center. Now, how do I combine the center of masses of large objects, not point-like objects? You see, here, this disk is just a collection of large objects. They are not point-like. Since they are not point-like, I cannot really use this expression without proving that I can. Now, the initial definition that we wrote, this is for point-like objects. If I have a collection of point-like objects, I can calculate its center of mass using this expression. Now here, I don't have a collection of point-like objects. This is no longer a collection of point-like objects. But still, I can prove that I can use the same expression. Now first, let's show that we can use the same expression. Now let me just assume two objects. This has a total mass m1, this has a total mass m2. This is the center of mass of the first object, this is the center of mass of the second object. Let's say this is the R1 is the position of the R1 is the position of the center of mass of the first object. R2 is the position of the center of mass of the second object. Now what I will prove is that the center of mass of the whole system will be equal to m1 times R1 plus m2 times R2 divided by m1 plus m2. Now this will kind of complete my claim that even extended objects behave just like point objects as long as we take as their position their center of mass. So we already know that if I have an extended object that is moving, then I can write its momentum as its total mass times a velocity, but this time it is the velocity of the center of mass that we had already proven. So that is one part of our claim that extended objects behave just like point objects, provided that we take the center of mass to describe its position and its motion. This will be our second claim. So this is, in fact, the expression that we use for if mass 1 and mass 2 were point objects located at their center of masses. Now, to prove this, we start from the definition of the center of mass. You see, this is, let's say, mi or I, 1 over the total mass. This is the general definition. Of course, to write this general definition, what I do, this is some trick that we will always do. If we have extended objects, we will just assume that they are made up of very small objects. We will divide them into very small segments. Each one we will be treating as if they are point objects. So I'm just dividing both of these masses into point-like volumes. So they are just collection of point-like volumes. For that collection of point-like masses, I can write the general definition of the center of mass. But now I can separate this sum into two parts. Our center of mass will be equal to mi or I, provided that mi is in the first mass, plus mi or I, provided that mi is in the second mass, divided by, well, the total mass of my system is nothing but m1 plus m2. So here I have, let's say, infinitely many terms. I just divide those infinitely many terms into two parts. One of them just contains the masses in the first mass. The second one contains the masses in the second mass. Well, we are almost done. This is nothing but almost the definition of the center of mass of the first mass. If we had divided this with the mass of the first mass, this would give me the center of mass of the first mass. This is m1 times r1. The same thing is true for this one. If I would divide this with M2, it would give me the position of the center of mass of the second mass. So this is M2 R2. So this is how we combine the center of masses of expanded object. If you know the center of mass of one object, then you can, of two objects, you can calculate the combined center of mass. And if we go back to our initial example, we had already shown that each ring has the center of mass at the origin, so the combined system also has the center of mass right at the origin, provided that mass is distributed uniformly. Now, this way of combining the center of masses of different objects, if you know the center of mass of one object and the second object, you can combine them. It allows you to calculate the center of masses of more complicated objects. For example, let's take an example. Where is the center of mass of this one? Let's say this is a disk of radius R1, this is a disk of radius R2. And the mass density is rho. This is surface mass density. Now, one way to calculate the center of mass of such an object is you can again just divide it into very small segments and just sum over them, this expression. Of course, when you are dividing into very small segments, you will be summing almost infinitely many of them, and it will eventually go to the definition of an integral, which will be in your homework, but at least in the class we will not be doing such examples. But we can use the trick of this here, this trick of combining the centers of mass of different objects. So you see, we have this object. Let's say radius R1. Where is the center of mass? Where is the center of mass of this one? It's at the center. But this object, I can just treat it as two separate objects. I just take this one plus this one. Do you agree? This whole mass is just this mass with this hole over there plus this mass over there. Where is the center of mass of this one? It's at the center. It's over here. So the center of mass, let's just put our origin to be here. So the center of mass of this one is at the origin. Now the center of mass of this one, you see our origin is somewhere over here. Let's just, for the sake of simplicity, let's move it a bit so that this object is right below. Now, where is the center of mass of this one? Let's say this distance is d. What is the position of the center of mass of this disk? So this distance is just d. So the center of mass of this one is just minus d times what? D times minus y hat. So 0 vector. This is the center of mass of this one. is equal to m1, the mass of this one, times our center of mass. This is what we would like to calculate. Plus m2 times d in the minus y hat direction. Now we know what our center of mass is. This is equal to m2 over m1 times d in the y hat direction. So it will be somewhere over here. It's not at the center, it should be lifted up. This is just one of the tricks that you can use to calculate the center of mass of object with cavities. Now this is a complicated shape. We don't know how to write down the center of mass. We don't know how to calculate the center of mass. Of course, you can just write down an integral to evaluate the center of mass, but the integral will be quite complicated. But what we can do is, we already know what the center of mass of this one is. We already know what the center of mass of this one is. So in a sense, you take the center of mass of this one, subtract the center of mass of this mass, and you obtain what is remaining over here. This is another way of obtaining the center of mass position of some complicated shapes. Questions?
Bu center of mass o boşluğun içinde herhangi bir yere denk gelebilme ihtimali var mı?
Do you remember there were at some point there were these fancy toys that they had these eagles. They had a beak. They had some wings like this, and you could just balance them on your finger. So this was basically the shape. This was the head of the eagle. This is the body. This is the tails, and then there was this wings. And what happened was, if you just hold it through the beak, it will balance. It balances mainly because the center of mass is right at the point of the beak. Now, if you put some mass over here, some additional mass, at the tip of the wings, the center of mass will move even further. It will not be in the mass. So it can go out of the mass. Your center of mass does not have to be in your mass. Let's do another example. You have some mass over here. Let's say it has a mass m. You have another mass over here, which also has a mass m. And their lengths are L and L. Where is the center of mass? Well, you see, the center of mass of each one of them, this is the center of mass of this mass, this is the center of mass of the other mass. So we have these two. We can now replace all of these masses as if we can treat them as if they are point masses at their respective center of mass. Now, if you combine these two masses, the center of mass would be, well, one thing, it will be on the line connecting them. And since they have the same masses, it will be right at the center of the line connecting them. It is not the center of the triangle. Usually it's not defined as the center of the triangle, though. But you see, the center of mass is not inside my mass. It is a point outside my mass. But of course, there has to be some cavity-like shape for that to happen. Because the center of mass, you can think of the center of mass as an average position. The average position of this object will be somewhere over here.
Söylediğiniz çok mantıklı hocam, anlattınız. Ama
Okay.
senin olmadığı bir yerde kütle merkezinden bahsetmek biraz garip geliyor yani.
Well, okay, so your friend's complaint is that we are talking about the center of mass in a region where there is no mass. Well, where is our average position? Over there, right? You are not there, I'm not there, but still our average position is over there. Or, I don't know, for example, if I want to just throw some gifts to the class, I would throw it somewhere over here. Whether there's some people over there or not, it doesn't really matter. It doesn't have to be inside my mass. And the velocity of the center, the acceleration of the center of mass is only and only determined by the external forces. If you remember what we were discussing since the beginning of the semester, we said that, okay, let's start with describing the position of the objects. We said that we would be dealing with point-like objects or with objects that do not change their shape and their orientation. Up to now, we didn't study the motion of objects if their motion is something like this. We always assume that they are rigid, they are not rotating, they make translational motion only. And then in that case, we said that, okay, to describe the position of this object, it was enough that we choose one point somewhere over here and specify the position of that point only, and that was enough. So that is what we did until this point. Now we are kind of relaxing that condition. Now we have seen by this discussion of the center of mass that what we have done up to this point is valid for any kind of motion. Even if this is not a rigid object, if I just throw it up, it will be rotating, it will be changing its shape, etc. So if you just take an arbitrary point, the trajectory of that arbitrary point will not be a parabola, for example. So if I just take this one, if you just follow the tip, if I just throw it up, the tip definitely doesn't follow a parabola. So it will be just doing some complicated motion. But if you could just mark the center of mass that we had just discovered, well, the center of mass is right over here. This point. Now, if you just throw this thing, do you see the white? Well, you have sharp eyes then. Okay, so if you can see that white spot, if you would follow that white spot follows a parabola, a perfect parabola, just as if it was a point mass. That is what our proof that the acceleration of the center of mass is always equal to the external force divided by the total mass of the object. It's a consequence of this property. Now, in the case of this stick, the external force is nothing but the total mass of this object, total weight, the force due to the weight. And we know that the force due to the weight of this object is we said that it was m times g. But even here, there is a very small assumption, in the sense that the total external force is not really m times g a priori. The total force, because the gravity will be acting on very small parts of this object. But assuming that this is not so huge, g is constant everywhere during the motion, so this will be equal to m times g, so the acceleration of the center of mass will be always equal to g. And we already had seen that if an object has this acceleration, this constant acceleration, it will follow a parabola. This equation tells me that the center of mass, the motion of the center of mass of this thing, will be a parabola independent of whether this object is rotating or not, or changing its shape, etc. The motion of the center of mass is only and only determined by the external force and nothing else. Now, this point will be important because the next step we will be discussing rotations. How can we describe rotation? What affects the rotational motion? But whatever is affecting the rotational motion will not influence the motion of the center of mass unless it changes the external force. You should just keep this point in your mind even when we are describing rotations. The motion of the center of mass is only and only determined by the external force acting on the system. Clear? Now, any questions on this one? Okay, unfortunately, my internet connection is not so well today here, so we will not be able to vote. But still, I have some questions for you. Okay, this is one question. So you go to a high place, you drop a stone. What happens to the momentum of the earth and the stone as our system? The stone is falling down. The magnitude of the momentum, or, well, okay, take a minute, then I will ask you to raise your hands. Ignore air drag, air friction, etc. Okay, so who thinks it's A? If I don't see enough hands, you will be just moving around in the class. A, B, 2, 3, C, a lot, D. Okay, so we have B and C. Why B?
Hocam şimdi taşın yere düşmesiyle dünyanın taşın üstüne doğru gelmesi aynı derecede doğru önermeler şimdi. O açıdan baktığımız zaman dünyanın momentumu biraz daha yani sistemi etkiliyor.
So because it has a larger mass?
Yes.
So your friend is saying that, okay, Earth is moving towards our mass, the mass is moving downward, but the mass of Earth is so large that it will be dominant. So that's why you say it is decreases in the downward direction, that is increases in the upward direction, right?
Yes.
So because the Earth is moving upward, and since its mass is so huge, the momentum will be increasing in the upward direction. That is B. Decreases in the downward or increases in the upward direction, they are the same thing.
But the question only says as it falls down, so time yere düşerken zamanını soruyor.
So while it is falling down. So let's just split the problem into two parts then. What is the momentum as it is falling down, and how does the momentum change after it falls down? So what happens after it falls down? So you are saying that after it falls down, it hits the ground, the momentum it decreases in the downward direction, but not before. So why do you say it decreases after the collision? Because it just stops.
Because I think it loses some of its energy.
So it loses its energy.
That's why I think it decreases after it hits the ground.
Okay, so your friend is saying that, okay, while it is falling down, the energy will be conserved. So the momentum doesn't change, it stays the same. When it hits the ground, it will lose its energy. So the momentum will change, and the momentum will decrease in the downward direction or increase in the upward direction. So after the collision, you agree with your friend. Before the collision, you don't. Okay, somebody else?
It stays the same all the time. While it's falling down, the earth is pulling down the object, and the object is pulling up the earth. So they have velocity in opposite direction, and the momentum does not change. And after it's pulled to the ground, and then it doesn't change again.
Why not?
Because when it's hit to the ground, it will go to the output again, and the road will.
I mean, let's see. Let's just imagine that you just jump down the cliff. Okay, you jump down the cliff. When you hit the ground, do you bounce back or do you just stay on the ground?
I think it will go to the output again.
Okay, we can test it. You can climb up the table and jump down and see if you will be bouncing up.
But I think it doesn't.
It doesn't matter. You're right. In that sense, you're right. But you don't bounce back. But it's not relevant anyway. Anyone else?
We know momentum conserved unless there's an external force. So, say if there's a system which Earth and rock is a shape system, there's no external force, there's no change in momentum.
During the fall or after the collision, you are saying that it doesn't change.
Doesn't matter because the system is the same, no external force at any time.
Okay. Anybody else? You see, when we were discussing the momentum conservation, we said that delta P is equal to 0 if the external force is 0. Of course, we can also say that delta P is almost 0 if the time that we are studying the system also goes to 0. Now, here we didn't say anything, for example, about the energy conservation. Energy might be conserved, energy might not be conserved. Whether energy is conserved or not, momentum is always conserved as long as Newton's third law is valid. Because energy momentum conservation is only based on Newton's third law. You are right in the sense that Earth is moving upward, but since Earth mass is so huge, its upward motion will be very small, almost negligible. It will be so small that the velocity gain of Earth multiplied by its mass will be equal to the velocity gain of the rock multiplied by its mass. The rock has a very small mass, but its velocity gain will be much larger than what the Earth gains. So the Earth is moving upward, but since its mass is so huge, its velocity gain will be negligible, almost negligible. The product of a huge number with a very small number will be just give you a normal number to cancel the momentum gain of the rock. So they will be exactly equal in opposite directions, the momentum gain of the Earth and the momentum gain of the rock, and they will cancel each other. Now, momentum conservation doesn't depend on energy conservation. They are unrelated conservation laws. Of course, they are expressed in terms of similar quantities like the mass and the velocity, but nevertheless, energy conservation is not a requirement for momentum conservation. Similarly, momentum conservation is not a requirement for energy conservation or non-conservation. Secondly, the momentum conservation is only and only a result of Newton's third law. As long as you have Newton's third law, momentum of the whole system here in this example, it is crucial to take the whole system because the momentum of the rock is not conserved. Momentum of the Earth is not conserved. But the momentum of the Earth and the rock taken together is conserved because in that case, all the action-reaction pairs are within our system. They are only internal forces. There are no external forces. And momentum is conserved as long as there are no external forces. Any questions? Any questions on, okay, this one? Well, this is basically the same thing. So who thinks it's A? You see, in this case, we have you and the Earth. You are jumping up. What happens to the momentum of the system? The momentum of the system, as you said, is always the velocity of the center of mass times the total mass of the system. It is always true. Okay, so your friend is saying C. Anybody else? It stays the same. Again, as long as we are treating the Earth and yourself and the atmosphere as your system, there are no external forces acting, ignoring, of course, the effect of the sun, the moon, etc. There are no external forces, and hence the momentum is conserved. So nothing changes. Whether there is dissipation or not, friction or not, this will only affect whether energy is conserved or not, but it has nothing to do with the conservation of momentum. Now, another side remark not related with this problem is, especially when you are solving questions, you always talk about this, the acceleration of the system, or in this case, we are talking as the momentum of the system. Now, whenever you are talking about the acceleration of the system, I would always understand the acceleration of the center of mass of the system, which is rarely what you intend to say. So just if you want to make some definition in your solution, in your homework, in your exam, or anything that you hand in to somebody else, make sure that what you mean by the thing that you write is clear. Okay, this is something more interesting. So here is the cart. It's at rest. There is no friction over here. And you just throw balls on this wall mounted on the cart. Will the cart start moving or not? Ignore the drag or any other kind of friction that will be acting on the cart. But of course, there is friction between you and the cart so that you don't fall off the cart. And here we will be assuming that you have these, let's see, you have many of these balls and you are just uniformly throwing it to the wall. Initially you are at rest, you are throwing it to the wall. Will you be moving? Will you gain some speed? After some time at least. Okay, so your friend is saying that it is just like trying to go use a sail with a ventilator, and he thinks that it will not work. It will move to the left this way. Okay, so why? So your friend is saying that initial momentum is 0. Eventually the balls are moving in that direction, in this direction. So the balls are carrying some momentum in that direction. The momentum should still be 0. So the final momentum of the cart should be in the opposite direction to cancel the momentum of the balls. So the cart will be moving in this direction. Any objections to this one?
Eğer topu fırlattıktan sonra topun işte duvara çarpma süresini kabul edersek hocam hareket etmez. Ama onu kabul etmesi önce
What is reality? Well, in nature, will that be 0?
çünkü onun efendim
In nature, will that be 0? In real life, will that time... So what you are saying is, if this time is 0, it will not move. Is that what you mean?
şimdi şöyle hocam aradaki şimdi önce biz fırlattığımız zaman önce friction'dan dolayı bir geriye hareket olacaktır hocam.
Okay. Which friction?
Static friction.
Which one? Between which? I mean, whenever you are talking about friction, friction is always between surfaces. In which surfaces? There are many surfaces over here.
Adamlar o kart
Okay, so the friction over here. Okay, so I just throw the ball in this direction. So the cart moves this way. Now, if we start from rest, I throw the ball in that direction. The cart will move in this direction. Okay, and then the ball will just go and hit the wall. And when it hits the wall, as it's bouncing back, it's exerting a force on the ball, on the cart, in the opposite direction. So after the collision, the cart will start moving in this direction, independent of the time scales. Whether the time of collision is very short, very long, it will not have any effect.
Şimdi şöyle olduğu için o süre ne kadar kısalırsa o kadar az olacak.
Well, you see, I throw it in this direction. Okay. At that instant, let's say I gain some speed v in that direction. After it collides and bounces back, I will, assuming that the collision with the wall is elastic. After the collision, my speed will be v in that direction. I will not stop. Initially, the moment I throw this in that direction, I am giving the ball a momentum p in that direction, let's say. Then the momentum of the cart should be minus p. Now, as the ball is moving towards the wall, it has a momentum p. After the collision, it has a momentum minus p. The change in the momentum of this ball during the collision with the wall is, its magnitude is twice p. So after the collision, initially I was moving in that direction with momentum magnitude p. During the collision, the ball will transfer a momentum 2p to the cart in that direction, because that 2p is the change in the momentum of the ball. The momentum of the ball changes by 2p in this direction, so the momentum of the cart should change by 2p in this direction. After I throw this, I had a momentum p in this direction. Now I have an additional momentum 2p in that direction. So I will move. I will have a final momentum p in this direction. If I throw another ball, of course I will slow down first. then when the ball hits the wall, I will accelerate even further. My momentum will increase, will keep on increasing as long as I'm throwing this away. Now, the next question we will be discussing after the break is how will my velocity change, assuming that I'm throwing masses uniformly? Not necessarily in this example, but you see, in this example, don't get confused with the presence of the wall. It's not relevant unless you are interested in the details in the time evolution of the velocity. Whether there is a wall over here is not relevant. The only thing that matters is what happens initially. The whole system is at rest. And finally, there are some masses moving in that direction, having a momentum in that direction. That is the only thing relevant. How do these masses are started to move in that direction? We don't care. They do not change anything. Because as long as they are moving in that direction, to conserve the momentum, the cart has to move in the opposite direction. Whatever might have happened in between. That is kind of the beauty of the conservation laws. You can ignore what happens in between. The only thing that's important is what you had initially and what you have finally. No, there's no external force over here. You see, the momentum of the whole system is conserved. It's always zero. But what happens is, since eventually the walls are moving in that direction, part of the system had gained the momentum in this direction. That means the remaining part of the system should have a total momentum in the opposite direction so that the total momentum will be zero.
Would it be possible even with the table tennis ball?
Well, you see, one of the critical things here is that with very little friction. Now, the forces that the table tennis balls will create will be very small. So you can, if you try to realize it with a table tennis, you have to make sure that the friction, the remaining friction is really, really small, which will practically, it will not be practical. But if you have a heavy ball, when you are throwing that heavy ball, and during these collisions, it will create a larger force, and hence you can say that friction will be negligible compared to that large force.
What may happen if you catch the ball?
What happens if you catch the ball?
The cart doesn't move.
The cart doesn't move. The center of mass should stay the same even. So in that case, what you say will happen. You throw the ball, you start moving in this direction initially. The ball is moving in that direction. The ball hits the wall and bounces back. So you start moving towards the ball moves towards you, you hold the ball, everything is back to its initial state. You are at rest. Okay, let's give a 10-minute break and we will continue after the break.